Welcome to another edition of E361 PreLab Guides. This is Hiren Rada. We are going to look at PreLab number 5 in this video. Okay, so let's bring up PreLab 5. Let's see. Okay, so PreLab 5 is about op-amps, part 2 of the op-amps, where we use the op-amp as an active filter and a comparator with speed control along with the BJT switch. So there are 4 problems or 4 questions in this PreLab. 3 and 4, right? Now, as always, of course, the background information in the lab write-up does have the explanation and also the equations. So I will briefly go over the questions, a little bit of the theory, and then the equations as you need to apply them. Okay, so let's take a look at question 1. So in question 1, we see that there's an op-amp circuit along with a capacitor and a resistor in the feedback path. Now, when you have this kind of circuit, if you think back to the passive filters we studied in E201, you would recall that a capacitor in the output loop would work as a low-pass filter. And it is the same function that the capacitor is performing in this op-amp circuit. This is known as an active filter versus a passive filter which is only R and C. The active component is the op-amp. So you not only have filtering from the RC components, but you also have active gain from the op-amp circuit. Also to note is that this is a inverting configuration, meaning the input is applied to the inverting terminal. So the output would be 180 degrees out of phase, all right? So a op-amp analyzed in the frequency domain will work as a filter. If you analyze it in the time domain, it works as an integrator. Of course, both of the things are happening at the same time. It is just the analysis technique that we choose to use. So in the time domain, the output of this circuit in phi-1 will be a integral of the input signal. In this case, VO and VI. So VO would be an integral of VI. And the output is shown in equation phi-9. And so you can see VO is integral of VI dt. If we analyze the same circuit in the frequency domain, we can prove that it works as a low-pass filter. Okay, it works as a low-pass filter, which is basically here in equation phi-4. Okay, let's see. So let's go back to the question here. So we need to derive VO or V out for RF, the feedback resistance of infinite value. Okay, so let's go guide right here. All right, and let's see. Seem to have lost. Oh, there it is. So the integrator equation phi-9 is basically, that's the derivation for V out. So it seems like simple, but students should absolutely practice and understand how we actually arrive at the answer. Okay, so for part 1 of the question, where we say we need to derive V out, well, that V out is the integrator equation phi-9. Okay, phi-9. Now, you're also asked to sketch V out for VI being a square wave. So if VI is a square wave, it should look something like this. Square wave. You are provided a amplitude value and a frequency value. Okay, one cycle, again from the basics of E201, would include one positive and one negative cycle, which is one time period. Time period T is equal to 1 over f, the frequency, which is given to you. The amplitude of the square wave is also given to you, and it's varying between plus and minus 10 volts. Plus and minus 10 volts. Okay. So once you have sketched out the square wave, all you need to do is plug in into the equation of right here, phi-9, and then let me bring that up. Okay. So we have the equation for V out. So you plug in the information into that equation, you reduce it, and you would obtain V out is equal to integral of Vi with some value and some value over here. Now, the limits of the integral should be equal to the cycle that you are involving. Okay, so if you are involving the positive half cycle, the limits of the integral would go from the limits of the x-axis, basically from 0 to the first time point, let's call it A, and then from A to the second time point would be the integral for the second portion. Now, whatever value you obtain, keep in mind, it'll be 180 degrees out of phase of Vi. Okay, so again, you should obtain, I won't give you the answer, of course, but you should obtain some sort of ramp input. Okay, so based on that information, your equation should have, should be a function of T. Okay, now that's it for problem number 1. Problem number 2, let's look at the question. So PreLab number 5, question 2. Same op-amp circuit, Vi is now given as √2 sine omega t, and RF is now given as 10 kilo ohms. And the question is, derive the closed loop gain. Well, closed loop gain is actually given in the lab write-up in equation number 5. So again, students should review the lab write-up and then practice. So if we go back to the lab write-up, and we see, start with equation number 5-1, then 2, 3, and then 4. Okay, so general closed loop gain VO over VI is given by the equation given here in 5-4. Okay, 5-4. Now, second part of the question. Determine the magnitude of V out in VRMS at the following frequencies. So if you want the magnitude, let's go to the equation for the magnitude, which is given right here in 5-6. Okay, 5-6. So the equation for the open loop gain is given in 5-4. Equation for the magnitude is given in 5-6. So magnitude of VO or V out is given in 5-6. One final question is to determine the cutoff frequency omega 0. Omega 0 equation is given in 5-11. Plug in the values, but keep in mind that you're asked the frequency in hertz. Omega is the angular frequency in radians per second. Frequency F is in hertz. So you have to use the equation omega is equal to 2 pi f. Okay, equation 2 pi f. All right, let's go to question number 3. All right, so question number 3 shows you a comparator. The comparator, an op-amp can be used as a comparator. So in this comparator, you are connecting a signal voltage at the inverting terminal, and the input to the non-inverting terminal is coming from a time-varying sinusoidal waveform connected to a bridge rectifier. You're asked to sketch V1 and VO. Okay, so the hint is you start with the sine wave, meaning you start with the 10 volts peak-to-peak AC signal, then determine what happens at the output of the bridge rectifier that goes into the comparator, and then you have V out. All right, so let's take a look at how we proceed with this problem. So first things first, comparator basically, as the name suggests, compares two signals and provides the output depending on the difference between the two signals. So in this case, we have a connection going to a connection going to a voltage divider network. So this 1K and 1K resistor form a voltage divider network. So you find the voltage, and let's call this Vx. Find Vx by applying voltage division. And you don't even need to do any calculation. In voltage division, two resistors are equal. You should be easily able to deduce what Vx is. So that is the voltage at the inverting terminal, which is Vx. Okay. Now, based on the connection, meaning the negative terminal and the positive terminal, the difference between the two, when it goes above the negative terminal, V out will go to plus 10, right? That is basically the input that's being applied. So when the input crosses, or not, the input V1 is larger than Vx, when V1 is larger than Vx, VO should go to plus 10 volts. When V1 is less than Vx, then VO should equal 0 volts. Okay, that's basically what a comparator will do. So now what we will do is we will sketch the input waveform. Now this is a standard typical sinusoidal waveform. Again, one cycle right here. That is the time period. Time period T is 1 over F. Students should be able to deduce or calculate what the time period is. The input signal is given to us as 10 volts peak to peak. You should be able to figure out what the positive peak and the negative peak values are. Once you have those, you'll have the input waveform. Now, this input waveform is applied to the bridge rectifier. So this input waveform is basically being applied as an input to the bridge rectifier. Based on your previous experiments, as well as the theory learned in 321, you should be able to draw out what the bridge rectifier looks like, or the output of the bridge rectifier looks like. Okay. Now, it doesn't mention here whether the diodes are ideal or not. If you wish, you can assume ideal diodes, or you can or if you wish, you can assume a practical diode with a voltage drop of 0.6 volts. Either way, students should easily be able to draw out V1. Once you have V1 over here, simply take a look at this table and determine what your output's going to be. Okay, and that's it. That's the output. Okay, problem number 3. Let's go here. Question. Okay, so we have a ideal BJT common emitter switch circuit. Okay, and we are asked to determine the value of V in for which the LED, well, device X is an LED, and it would turn on. Forward bias voltage for the LED is given as 2 volts. You're also asked to calculate V out and IRC and also IR1 through that base resistor when the LED is on. Okay, so let's look at how we can do that. So all right, so in this diagram, the circuit diagram, we have a NPN transistor, NPN BJT. The input signal V in is digital, meaning it can only take 2 values, either 0 volts or 5 volts. Okay, when it's 0 volts, the base emitter junction is off. There is no current flow through the transistor, and so the LED is off. Well, and when the input V in is plus 5 volts, the base emitter junction is on. BJT has current flow. When you have current flow, well, what will happen? The LED will turn on. Since this is an ideal BJT, we can assume VBE, the forward bias voltage drop, would be 0.6 or 0.7 volts. And because it's ideal, we can also say that VCE, meaning the voltage between the collector and the emitter, would be completely equal to 0. And if that's the case, well, then all you need to do is to apply KVL in the output path. Now, in the output path, we have 4 voltages. We have the 10 volt DC supply. We have the forward bias diode voltage, so VD. We would have the voltage drop across the collector resistor, and we would have VCE. And they should sum up to 0 volts. And of course, VCE, we have already confirmed, should be equal to 0. So you plug in the values and you solve for IRC. IRC is, of course, basically the collector current. So IRC is the collector current. That's where the resistor is connected. Similarly, you apply KVL in the input path to calculate IR1. So KVL input path, calculate IR1. You can write V in, you have IR1 times R1, and you have VBE, all summing up to 0 volts. I'll leave it to the students to determine what voltages add up and which ones are subtracted. Once you solve for those, you should be able to calculate IRC and IR1. And also V out. Think about where V out is taken from, and the answer is, well, it's already given. Well, that is PreLab number 5. Reach out to your professors, reach out to me if you have any questions, and well, good luck.